Water, especially drinking water, is one of the most important things for humans. This is why the Department of Health mandated a yearly water testing for all establishments and monthly for all water suppliers in every city in the country. The testing procedures up to the releasing of the results can take up 1 week. There are two main parameters of water potability, mainly the physicochemical and the microbiological. In the physicochemical, there are three mandatory parameters which are tested. The pH level, which determines the degree of acidity and alkalinity of a water, which is done using electrometric method. Next is the total dissolved solids, which measures the total suspended solids in a sample, which is done using gravimetric method. Next is the turbidity, which is the measurement of water clarity, done using the nephelometric method. Meanwhile, in the microbiological test, it comprises of three sub-parameters. The first two are the indicator organisms, which is the total coliform and E. coli. They are simultaneously counted using membrane filtration technique. Next is the heterotrophic plate count, which is processed using the pour plate method. The bacteria took about 2 days and the counting can take up to several hours to a day, according to Ms. Gemma Galanza, the head microbiologist of Optimal Labs, Lipa. And due to the mandatory water testing annually and monthly, the amount of sample piled up for the laboratory technicians to count and to measure. With the testing being prolonged due to the processes, the proponents came up to the idea of decreasing the testing time by automating the process of acquiring physicochemical parameters using sensors and automatically counting the bacteria colonies using image processing and evaluating them all using different algorithms. The project will be significant for the lab technicians, which will increase their accuracy and efficiency, and for the customers to yield better results and reduce their waiting time. These are the comparison of the conventional and proposed methods. To better understand this system, here is the conceptual background of the system. There will be 4 inputs. The first one is the water information. The next 2 are the agar plates for the microbiological counter. The next one is the input of water raw sample, which will be input to the physicochemical test. The physicochemical test and microbiological counter will be connected to the Raspberry Pi microprocessor, which is in charge of image processing and the evaluation, and the touchscreen LCD display for the graphical user interface. It will then output an updated water result to the database in the cloud database.
The system is composed of 3 different parts, which are the input system, the processing system, and the output system. The input system is composed of the GUI, the image captured from Raspberry camera, and the data from the sensors. For the processing system, Raspberry 4 acts as the microprocessor, which is used for image preprocessing, machine learning, fuzzy logic, and the control of the GUI and the Arduino Uno. For the output system, the water sample grading system will be displayed in the GUI in a 7-inch LCD touchscreen and stored water testing results in the cloud database.
The CAD design of the project is made to visualize the component placement inside the hardware. The first figure is the isometric view. Here you can see at the top part, an LCD screen is placed for the user to access and control the system using a graphical user interface. Next is the front view, where the physicochemical testing mechanism is placed. It is composed of a conveyor belt which will allow a beaker to go inside and a set of sensors that will dip into the beaker with water and measure its physicochemical parameters. Last is the right side view, where the microbiological testing takes place. Here you can see the 5 petri dish slots. It is rotating so that the Raspberry camera above can capture the dishes individually. Now, you can see the actual hardware of the project. Here is the front view, the conveyor belt and the sensors above. And here in the right side part is the 5 petri dish slots.
To better understand the software, here's the general flowchart of the whole system. First, you will start And then you will prepare the samples, and then you will ask what test will you be taking. If you take physicochemical test, it will ask you to insert the samples, and then the sensors will determine the pH level, turbidity, and total dissolved solids. After which, it will be supplied to the machine learning and physiologic evaluation, and it will display the results and end. And if you answer no to the physicochemical test only, you will be asked again if you will test microbiological test only. If you say yes, it will ask you to enter the corresponding inputs, which is the dishes, and the system will capture the image on the petri dish and count the number of bacteria using the image processing procedures. The result will then be subjected again to the machine learning evaluation and physiologic evaluation. Now, if you choose both, it will undergo the same process, and the after result will still be subjected to the machine learning and physiologic evaluation.
So for the image processing, the initial plan is the image acquisition using Raspberry Camera V2. But because of the enhanced community quarantine, the group decided to use cell phone cameras to take pictures of the petri dishes. After capturing HPC plates, it will be attached to the GUI, or the image will be attached to the GUI, and then the system will ask if the number of attached or acquired image is equal to the number of input HPC plates. If no, the image capturing will resume, while if yes, the acquisition and attachment for TC E. coli dish will be the next step. After completing acquisition of all images, the RGB to HSV conversion will proceed. Then the system will determine if the image is an HPC plate or not. If HPC, binarization or grayscaling will be done before proceeding to thresholding. But if the image is TC E. coli dish, then it will directly proceed to thresholding. After thresholding, background elimination and noise removal will take place. This step will be used to remove unwanted subjects in the image for easier analysis. Then after all this process, water shedding must be done to divide overlapping colonies if there are. But if there are no overlapping colonies, then the image can proceed directly to segmentation and finally the counting. So for the evaluation of colony counting software in an HPC plate, so let's say this is the original image. So the first step is RGB to HSD conversion. Then it will proceed to grayscaling or binarization, wherein the color of the image will be converted into just shades of gray before entering the thresholding process. Thresholding process, the process here is the color of the image will be converted into black and white while increasing its intensity, so that the analysis of the image will be much easier and the unwanted noises can also be removed. Then next is noise removal and background elimination. Then as we can see here in the thresholded image, there are overlapping colonies, which means that water shedding must be used so that we can divide overlapping colonies equally for more accurate results. Then after water shedding, we will proceed to segmentation and finally counting. So for evaluation of colony counting software in TC E. coli dish, let's say this is the original image and the goal is to evaluate red colonies, blue colonies, and finally evaluate both of them to determine if the colony is total coliform or E. coli. So the first step in the process is color space conversion from RGB to HSV. Then we will not be using grayscaling since color is very important in this parameter. Then after conversion, we will be using thresholding. Thresholding is used to increase the color intensity so that we can easily count or we can easily determine what to count and what not to count. Then after thresholding, noise removal and background elimination will take place. After noise removal and background elimination, there will be water shedding if there are overlapping colonies. Then if there are no overlapping colonies, We will proceed to segmentation and finally the counting.
Here's the fuzzy logic algorithm. This is its flowchart. First, you have to input the parameters. By inputting the parameters, you'll be arranging the range of the parameters and set the values and set the labels for it. Now, you have to put now the antecedents for the inputs and the consequence for the outputs. This is for the fuzzy logic to easily identify the inputs you have put in and the outputs you want to gather. Next is to set a membership function using Gaussian membership function. Now, this is the one used in the project. As you can see, it is defined by the ranges of the input parameters. Next is to set the fuzzy rules to which is pass and which is fail. After that, you will create and simulate a control system coded using the scikit library, fuzzy library in scikit. And then you will compute and crunch the numbers using these codes. After which you will have an output. You will judge the output if it's in with the standard or not. If not, you have to recheck your code in the input range and the membership functions. But if it's correct, you can now display the result. This is the machine learning model training algorithm. First, you will start with loading data in a CSV format. And then you have to define the machine learning models. In this case is SVM, ANN, and KNN. And then compile it in using a scikit library. Now you have to split the data into 3 ways. In this example, it is split in 70-30 data split. And you will fit the models, evaluate them. Upon evaluating, you will observe their testing results if they reach 90%. If not, you have to perform another feature selection or adjust your codes. If yes, you will proceed and pick the model with the highest accuracy to be used and to be embedded in the system. This part is the machine learning model training for every model, SVM, ANN, and KNN.
The system will be controlled using the graphical user interface. In the first page, the user can select whether to log in, to register a new account, to seek instructions using the Help button, or to read about the project and the proponents. Now, when the user successfully logs in, the menu page will be shown. It will allow the user to add a new water data, update an existing data file, view results, or log out of the account. In adding a new water data, the user will be asked to fill out the customer information. Next, he must select what type of test to perform according to the customer. If physicochemical test only is selected, the user will type manually the physicochemical values. If microbiological test will be done, the user must select the number of HPC Petri dish to be evaluated. To perform the image processing for bacteria counting, the user must attach the photos of the Petri dish. Same procedure in updating an existing file, except the user will input the date before testing. In viewing the results, the user can select the customer name and see the compiled results in the next page.
Due to the pandemic disease that led the President to declare an enhanced community quarantine, or ECQ, for the whole Luzon area, the functionality of the conveyor and sensor holder, which were used for physicochemical tests, and the rotating platform for microbiological tests were not tested. For the evaluation of the functionality of sensors used in the system, the pH, TDS, and turbidity sensors were only calibrated before the declaration of ECQ. But unfortunately, the proponents were not able to test its functionality. The proponents was unable to test the functionality of the Raspberry camera for image acquisition because the prototype is currently not in the hand of the proponents, which where the camera was fixed. To test the program made for microbiological test, the proponents took images using camera of the phone to acquire data.
So for the microbiological testing, there will be 2 settings in the GUI. There will be 1 input HPC plate and 4 input HPC plate. So for one input HPC plate, there will be one HPC plate and one TC E. coli plate. So the final output for this is count. Both images will undergo image processing. The count will be coming from these images. The count that will be generated in these images will be the input for the image classifier or the machine learning classifier or the fuzzy logic. Both fuzzy logic and machine learning classifier will decide if the images will pass the test or fail the test. And these are the generated results. For the 4 input HPC plates, there will be 4 HPC plates and 1 TC E. coli dish. So there will be a different approach in this one. Still, all images will undergo image processing. Since there are 4 HPC plates, each count of HPC will be multiplied to its corresponding dilution multiplier. Then all products will be added to get the final average count, and it will be the heterotrophic plate count. Then same process will be done for TC E. coli dish. Then still, the counts for both HPC, TC, and E. coli will be the input for the machine learning classifier or the fuzzy logic, which will decide if the system or if the images will pass or fail the microbiological test. And these are the generated results.
This is the evaluation of machine learning algorithm for all the models and different data splits. This is the training model for the physicochemical parameter and microbiological parameter with 7-30 data split in SVM, and it's the one highlighted is the corresponding testing accuracy. Next is the 80-20 data split for SVM, 90 and 10 data split for SPM. Next is the k-nearest neighbor with 7-30 data split for both microbio and physicochemical. Next is the 80-20 data split for KNN. Then the 90-10 data split for KNN. Next is the artificial neural network with 7-30 data splits, and followed by the 80-20, and then the 90 and 10. Now this is the summary of the physicochemical parameters. As we can see, the highest accuracy came from the 70-30 data split of artificial neural network. And for microbiological, the highest is from ANN, KNN, and SVM. Now this is the summary of the parameters that will be finally used on the project. ANN will be used for physicochemical and microbiological. This is the fuzzy logic classifier evaluation. These are the 6 membership functions and graphs set by the fuzzy logic code. Now, to better understand this, the one with the higher degree of truth will be ruled out. In this case, the HPC count with 0 to 500 is ruled out as few. And the one with a 500 and above has a degree of truth in many. Has a higher degree of truth in many. Now, this is the fuzzy logic classifier evaluation. We've tested 12 different tests of samples to classify its effectivity, whether it pass or fails under the boundary or over the boundary, based on the Philippine National Drinking Water Standards. In this case, these are the inputs, and the one in the green will be the judgment. Successful test, another successful test,
To test the functionality of the GUI, the proponents made sure that the user can register and log in to access the system. Here you can see that the proponents successfully created 5 new accounts. This is to test the registration of the GUI. Next, the proponents log in the 5 accounts to test the login functionality. It can be seen here that the accounts made can be successfully used to access the system.
Testing for accuracy and efficiency of the host system. For the accuracy, the proponent stated that the Cosmolab's measurements will be used as the true value and the project's assessment will be the approximated value. The accuracy for physicochemical and microbiological tests must be both compared to the results from the Cosmolab. Unfortunately, due to the ECQ, the tests which will be done by the Cosmolab were affected. Thus, the proponents were unable to test the system's accuracy. For the efficiency, the proponents stated that the time of the technician from the Cosmolab will be used as a true value and the project's time operation as approximated value. The efficiency of physicochemical and microbiological tests must be both compared to the time from the laboratory. Unfortunately, due to the ECQ, the tests were affected, thus the proponents was unable to test the system's efficiency. After completing the design and development of the water potability tester, the following statements were concluded. For the hardware, the researchers managed to develop a hardware which can acquire the water potability parameters using the Raspberry microcontroller. However, due to the events of the pandemic, the hardware was left behind in an apartment when one of the proponents evacuated. And due to the absence of the hardware, the camera as well as the sensors which were attached to the prototype were left behind. The microbiological parameters are obtained using an image taken by a phone camera and subjected to the image processing software developed by the proponents. While for the physicochemical test, the proponents failed to acquire the specific parameters using the sensor. For image processing, the proponents were able to finish the image processing techniques such as color space conversion, grayscaling, thresholding, background elimination, noise removal, and image segmentation to count the number of the colonies. The counts gathered by the system became the input of the fuzzy logic and 3 machine learning models. For machine learning, the proponents managed to develop 3 machine learning models as part of the development of the system. They are SVM, KNN, and ANN. Initial training was performed using the 730 data splitting. The models were trained by using different data splits, 80-20 and 90-10. With the results of the training, the proponents select ANN model with 70-30 data splitting in both water potability parameters as the highest testing data accuracy. For fuzzy logic, to counter-check the evaluation of the machine learning models, the proponents developed a fuzzy logic classifier using SK fuzzy library in Python programming systems for both microbiological and physicochemical parameters of the water. The parameters range were set based on the Philippine National Standards for Drinking Water 2017. For the graphical user interface, a graphical user interface was developed to control the system and display certain information. It allows the user to register, log in, add new file, update existing file, choose what test to be done, and see the results of their chosen test. For cloud database, a cloud database was developed by the proponents which enables the user to log into the cloud and view the results done in the system. For the data gathering data of water samples from an authorized water laboratory testing center with the contents of microbiological and physicochemical parameters with an evaluation of its results whether pass or fail was unable to be done because of the undesirable events. The proponents as well as the authorized water laboratory testing center were affected by the implementation of ECQ and it's difficult to gather sample data. For overall accuracy and efficiency, as said earlier, with the implementation of ECQ, the group encountered a problem with the availability of the hardware, thus affecting the overall testing of the system. The group were unable to evaluate the accuracy and efficiency of the host system. Since the Cosmolab is also closed, it is impossible to get the test results from the laboratory that will be compared to the results of the system, as well as the time of the laboratory technician to test the samples that should also be compared to the time of the project operation. To further improve the system, the following are the recommendations of the proponents. The fuzzy logic can be used as a sole classifier of the system since it is more accurate than using machine learning. If machine learning will be used to classify the data, it is recommended to have more samples in training the system to increase its accuracy. Multiple cameras may be also used to capture Petri dishes all at the same time to increase the efficiency of the system. The system may be redesigned to make the hardware more compact. And lastly, to make it easier for the customer, a PDF file of summary of the results may be sent through email.
So before we start the testing, here is the water potability grading that the proponents created. So let's start by running the graphical user interface. So let's try to log in without and using an unregistered account. So as we log in, an unregistered account, it will determine that it failed, and then you will register, and then we'll try to register an account. So let's type the name, the username, and set the password. So enter. So now we have a registered account. Now let's try to log in using that registered account. So enter. Login successful. So let's try to add a new file. Lipa, input the name, email address, contact number, and the date. So you'll add the specific informations of the customer so that it will appear in the results in the cloud database. You can easily find out the profile of the customer. So create. Now you will choose what type of test you will be testing. Is it microbio, both, or physicochemical only? So let's try both with 4 petri dish per HPC. So let's input the images for HPC. Since we don't have the Raspberry camera because it's in our hardware, we will just going to attach the image from the folder. So let's attach the TCN E. coli with no colonies. So once you click proceed, the GUI and the image processing code is already running. That's why it takes longer before physicochemical test ask you what type of values will you input in the physicochemical. Usually this process takes more than 10 seconds if we have a lot of HPC to count. So after which you will ask to input the dummy values of the physicochemical. We're going to input dummy values because we don't have the sensors. So these are the results. We're going to save it and to notify us that it is saved successfully. So let's try to update the data of Lipa. Once you update, you will type a new date for testing. So let's try to input a new date. And you will be asked again what type of test. Let's try both again. And then with 1 petri dish for HPC. So the reason why there's 2 options if you can add 4 or 1 petri dish is because the testing varies per water testing facility. Some test 1 HPC dish only, some test 4 HPC dish only. So let's try to process again. Now it takes time. And then you'll input the physicochemical values because we don't have the sensors to gather the different water parameters. So you'll just have to input the dummy data, and then this will be subjected to the fuzzy logic evaluation. Now here are the results. Microbio passed, but physicochemical failed, so it's level 2 non-potable. Save, and then let's try to update again an existing file for Lipa. Add the new date, and then let's try microbiological only. Let's try another one for for both micro and physico. But this time, let's try to attain a level 3 non-potable which has passed HPC but failed TCN E. coli. So there, I think it's a pass HPC value because it has fewer colonies in there. So the blue colonies are the E. coli, the red colonies and the blue colonies are the TC. So you have to input the pH values. So let's try to add a pass value for the physicochemical. So as we can see, we have failed micro and pass physico, so it's a level 3 non-potable. So let's try another test in which both parameters failed. So let's try one petri dish for HPC but with failed remarks. Let's try the one with a high number of HPC. Now, when the HPC colonies are higher, the process takes longer. I will explain it later when I show you the image processing code. So let's try to process. Again, this process takes longer because it has a higher number of colonies in the HPC dishes. So you have to input the physicochemical. Let's input field data. Both fail, so it's level 4 potability grade. So save and let's try to view the results. So as you can see, there's the profile of Dela Lipa. Then you will see the 4 tests that we've made. Level 1 potable, level 2 potable, up to level 4. And its corresponding values per parameter and the date. So let's try to update again Dela Lipa. But this time, let's just take microbiological test only. So let's try to input a new image for the HPC. So let's try this one and another image for TCN E. coli. Let's try one with one E. coli only, one blue colony. So the result must have one TC and one E. coli on the result, and it should fail in the micro. So again, the process takes longer because the image processing is already taking place in this part. So there's no grade for physico and overall grade because we only test microbiological. So let's save it. So let's try to update now with physicochemical test only. So we'll just have to input the data. Now this process takes shorter time because there's no gathering of data using the sensors and it is only subject to the fuzzy logic algorithm. So passed but no micro and no overall grade. So let's save it. So let's view the results. As we can view on the results, it's there, no data for physico and no data for micro if we choose microbio only. So there's the database and the local host in the GUI. But later I will show you the database at the cloud. So let's try to add a new file, Jollibee Tambo. Let's just see if the data will stack up in the view results menu. So input the email, contact number, the date of testing. So with this kind of platform, the laboratory technician can have an easy access of the test that he or she will be making. So let's try 4 petri dishes for HPC. Let's select the one with the higher number of TCN E. coli. Let's try images 1, 2, 3, 4. So you can see you'll just attach TCN E. coli. Let's input random pictures. Then process. Again, this process takes longer because we now have 4 petri dishes of HPC which have higher number of colonies to be counted. Just processing. Okay, I have to input the physicochemical values. And then you'll click proceed. So that's the grade, level 4 non-potable because both parameters failed. So save. Let's see in the view results. So we can see that there's Jollibee Tambo. So the other parts of the Go is help, where you can ask for instructions, and then about, which is the description of the project and the proponents. So we're going to exit and we're going to access the cloud database. Let's see if the test that we've made is already there. So let's try a failed username first, so that you can see that there's a prompt that the username is invalid. So there's the prompt, and then let's log in with the correct account. Once you enter, you can see the data, Dela Salipa and Jollibee Tambo. Let's see Dela Salipa, the test we've made. We've made 6 tests. There's the data. For Jollibee Tambo, we've already test once. So there's it, the cloud database. Now I will show you the code for the image processing. This is the image processing code, and let's just evaluate if it really can count the inserted data in the GUI. So this is just for testing. First, we will just going to test the images that's it's currently on the folder of HPC pass. So the code of this extraction for HPC is also with that folder. So let's try with this one. Let's import the photos. So this is the first photo. As you can see in HPC, the loading of and the processing of image is really longer because it has more colonies to be counted in there. So I already ran the code, and I will just show you the image that I evaluated. So this is the image that I evaluated, and then these are the processed image. So the blob, the grayscale, the thresholded one, and the segmented one. So you can see that there's already the count, and you can see it on the command prompt also, together with the result page with the red dots on it. So yeah, HPC passed 154 colonies counted. So let's try another one. Again, the loading of the image takes longer because of the number of colonies that are present. The more colonies in there, the longer the processing time. Okay, so these are the results. Again, that's the blob of the dish, grayscaling, and thresholding, and the result, which is 285 as listed. It is also displayed on the command prompt. HPC pass because it's below 500. Again, this is just for the testing of the image processing, if it's working. So here's another one. Blob, grayscale, threshold, and the result 187. Again, it's also passed. Let's try another one. Image 12 in the folder of HPC pass. I don't know, let's just try from HPC fail. So I'll just edit the code for the folder and processing image 1. So The failed one takes longer because it has more colonies to be counted there. You'll see later when I'll show you the results. So this is also the reason why after you input image, it takes longer before you input the physicochemical parameters in the GUI, because the image processing is already taking place when you input the image and the graphical user interface. So these are the bluff, the grayscale, the thresholding, and the result, which is 871. It is above the standard, which is 500 only. So as you can see, there's a lot of colonies that is counted. So let's try again another one. That's the result. Let's try E. coli and TC. So I changed the folder. So that's the first one with no colonies in there. It it uh it counts more faster than the HPC because it has less amount of colonies to be counted. So that's 3 tests already. Again, here's another test with 1 red and 1 blue. You can see in the display that they're counting the red colony and the blue colony. It is what identifies what the E. coli and TC is. So we have 4 red and 4 blue. Another set of tests for TC and E. coli. Once there's a colony in TC and E. coli, it's already failed because that's the standard. So that's it for image processing. So this is the evaluation of the fuzzy logic algorithm in case you are wondering what will happen to the image and the dummy data that you input on the GUI. So for example, the count is 30 for HPC and 0 E. coli and 0 TC. For physicochemical, you input 30 in turbidity, 6.5 in pH, and TDS of 40 also. So let's try to run. In the command prompt, you can see that results for individual is also here, as well as at the bottom is the per parameter test and the overall water judgment, which is pass. This is just for the testing of how the GUI works, how the fuzzy logic works. So let's try again another. Let's try 600 HPC, 2 E. coli, and 4 TC. For turbidity, let's try 60. TDS, let's try 700. And pH, let's try 13. So the results must be failed this time because these are some failed values. So as you can see, there's a lot of failed tests in here in the results. So let's try another one. Let's try 501, 0, and 2. Let's try for turbidity 51, pH 8.5, TDS 601. These are the edges of the standards. For the HPC, it's 500. For TDS, it's 600. So let's see. The HPC should fail. TC coli should pass. TC should fail, but E. coli should pass because it has 0. So as we can see, the judgments are correct. So let's try again another past value. Let's try 200 HPC, 0 E. coli, and 0 TC, because you only have past TC and past T. coli when you have no colonies counted. For turbidity, let's try 30. The pH is 6.5 to 8.5, so I'll try 7. Then for TDS, it's maximum of 600, so let's try 400. So the judgment must be passed. Okay, so this is the correct judgment, as we can see. So this test is just for the representation and not for the actual, because this is not the one attached. This is the one that is used as the code, but this is not the one that is already attached to the GUI. We're just running this for testing. So let's try last one. Let's try the mix of pass and fail values. So TDS, let's fail it with 700, pH with 14, but pass turbidity with 20. TC should be always be greater than E. coli. So let's try 5 and 0 E. coli. And then let's have a pass HPC 300. So let's run. It should be pass, pass, fail. Pass, pass, fail, pass, fail, fail. And then failed biological, failed physicochemical, and failed water potability judgment. So that's all for fuzzy logic.